Engineering 305, Chapter 6, Section 1 through 4, torsional loading of shafts. This is the short version. I recorded this lecture and I spent 35 minutes and derived the equations and I posted it. You can see that one. And I woke up this morning and thought, that's really not maybe the best way to present this. Maybe there's a better way. And so I'm actually going to use exactly the same slides, but I'm going to get rid of a lot of stuff. And so you'll see what we're going to do. The learning objectives have not changed. We want to be able to calculate stresses and deflections. And this is very similar to, and this video is going to stress the parallels to what we did with axial systems. But this is now calculate stresses and deflections which result from torsional loads on round or rectangular solid sections. So we get these equations, a lot of stuff. Don't get overwhelmed, certainly. I've got apparently the wrong pen for this computer. Hold on one sec. Let me get the right pen. Yeah, that pen. Okay. So there's my material property. That came from chapter 4. That's the shear modulus is equal to the shear stress divided by the shear strain. And then here's the only other two equations that I really want you to focus on. This TC, that is the stress at the outside. If I have, that's going to be my maximum stress. And that tells me my stress as a function of the force applied, but now it's a torsional force, so it's a torque. And then C, that's the distance to the extreme fiber, and J. J is this new way that material gets distributed, and I go through that derivation, but bottom line, here's J right here. If the radius on the inside is 0, then it's just pi over 2 times the radius of the outside to the 4th. That's what you need in order to get the stress, and that's our first equation. Here's our second equation that I want you to know. And that is theta is equal to TL over JG. That is similar to delta is equal to PL over AE. And we're going to examine this in the next slides. And I have a lot of blank slides because I'm just not covering the material that I was going to. But those are the big takeaways from the first part, for the first half of chapter 6. I want to point this out. Torque isn't real. What we really have is forces that are applied at a distance. This is kind of a philosophical. Watch it on the other one. And then we think about twisting a shaft. We only need to do this if we're going to derive the equations, and then we wind up integrating. And now I've got a blank slide so I can look at. I want to talk about the parallels between this information in chapter 6 and what we did in chapter 5. So in chapter 5, start with what we know. Stress was equal to force over area. And now I've got the shear stress is equal to TC over J. Let me rewrite that C because it looks like it's got something else going on. It's TC over J. And now T is related to a force, right? But it's a torsional force, so it's equal to a force cross a distance. So it does kind of have some geometry in it, but not really. That's just how that torque is applied. And then this C over J, this is a geometry term. Rushing through it. This is a geometry term. And so it's similar to force over area. This is now a torsional force divided by, well, this J over C, but yeah. Okay, the other equation that I've got, what I had last chapter for axial loads was my deflection is equal to PL over AE. And we could have used an F. We could have, it's just a symbol there. It's a placeholder, right? Well, P is good. It gives me that acronym play. Now, in a rotational world, I'm measuring theta. That's how much does this twist? And that is equal to TL over JG. And this, we got to go back and start taking a look at this torque, and I'll start drawing some lines. The force and the torque are the same idea. That's how much I'm pushing, how much I'm pulling, how much I'm causing it to twist. The length is important in both equations because as the part becomes bigger, the deflections become bigger. So you shouldn't be surprised that there's a length in the numerator of both. As the length grows, delta grows. As the length grows, theta grows. Then I've got my I've got a geometry term. This is my geometry. Maybe I should label the ones up above too. Geometry, this is a force. Length is the length. And that geometry is important because that determines how I absorb that energy, how I absorb that load. And then lastly, I've got E, and that's a material property. And we're going to do the exact same things that we did in chapter 5. Oh, and I guess I should. Those are my deflections. And I think this is the key slide for this stuff, that this is what you need to know for sections 1 through 4. It's this equation, TC over J and TL over JG. We're going to go do the same things. We're going to hit a situation. We put a torque on a bar, and how much does it twist? And that's a displacement question. So we go to our displacement equation. We're going to say if we put that torque on the bar and it deflects this much, what's my stress? Can I tolerate the stress? Yeah, that's a great question. So now we'll have an allowable shear stress. But this is the first sections of chapter 6, and we're going to continue on. We're going to do torsionally, statically indeterminate. We're going to do stress concentration factors for items that are in torsion. And then we've got one new thing that we'll wind up doing, which is now talking about power transmission, because that's what we do with shafts. We move power from one location to another. And so we'll talk about power translation, and that comes up. We get one more equation to do that. But that's really the rest of the chapter. Now, if we had gone about it the other way, you can see how many slides I'm not using. Okay, there's an empty one. That's 11. Oh yeah, see, this is where I started deriving stuff. Nope. Oh, did you want to do a derivative or an integral? Nope. So the next thing we're going to do is example problem 6.1, and that will look at, we're going to determine the torques transmitted, that's capital T, by the cross section in the intervals. And well, look, it actually gave us the answer right there, but that's okay. I think I'll have to read that later. Anyway, we'll jump onto that. That's the next thing we're going to do. This is a much shorter video. I hope you learn more from, or as much from this one as you do from the other. Take care. Have a great day. Remember, there's more coming.